scientific dust collectors, presenting ASHRAE Standard 199, the standard of dust collector performance. Brian, over to you.
The dust collection industry has been around for many years and operated without an industry-specific standard to address the performance of the different types of dust collectors. Instead, the dust collection industry was limited to stating the MERV rating of the filter elements. In 1987, the American Society of Heating and Air Conditioning Engineers, also known as ASHRAE, developed Standard 52.2 and the Minimum Efficiency Reporting Value, or MERV rating. This standard was established for the HVAC after-filter market to define and rate the filtration efficiency for filters in industrial HVAC systems. Filters are rated on a numerical scale of 1 through 20, with 1 being the lowest efficiency and 16 being the highest efficiency for industrial HVAC. Filter ratings above 16 are typically used in hospitals, clean rooms, and other hazardous areas. While the MERV rating is wonderful for the after-filter market, it has problems applying to dust collection. In a pulse jet dust collector, filters are repeatedly pulse cleaned periodically with compressed air when a dust filter cake builds up on the surface of the filter media. The MERV rating exclusively focuses on filtration efficiency of a filter element under controlled laboratory testing. The testing is designed to mimic HVAC systems, and HVAC filters are not designed to be cleaned. They are designed to be replaceable. On June 1, 2016, the Standard 199 was published as a joint venture between ASHRAE and the American Standards Testing Institute, also known as ANSI. Standard 199's purpose was to provide a quantitative laboratory test method for determining the performance of pulse jet dust collectors using a known test dust. Standard 199 applies to all bag, cartridge, or envelope industrial dust collectors that recondition the filter media by using a pulse of compressed air to discharge the dust filter cake from the filter media while the air cleaning device remains online. The testing methodology that Standard 199 takes is a black box concept, where the dust collector is viewed in terms of its inputs and outputs. The test procedure is not concerned with the internal operation of the dust collector, rather the actual performance of the dust collector itself. The Standard 199 test procedure consists of 6 stages that must be completed continuously without stopping the airflow. Stage 1 is the initial dust loading. This stage loads the filters in the dust collector to a predetermined differential pressure, or DP, with the pulse cleaning off. Once the predetermined DP has been reached, the test enters Stage 2, which is the initial dust loading with on-demand cleaning. This stage turns the pulse cleaning on in the on-demand setting. On-demand is when the cleaning frequency is determined by a high DP and a low DP. Stage 2 lasts for 4 hours. After stages 1 and 2, the initial dust loading has been completed. The following stages replicate real-world dust collector operation and performance. Stage 3 is the dust loading with continuous cleaning stage. This stage changes the pulse cleaning frequency to a continuous operation based upon the pulse on-time setting. Continuous cleaning is the most common form of pulsing controller in dust collection today. Stage 3 lasts for 24 hours or until a predetermined maximum differential pressure is reached. Stage 4 is the final dust loading with on-demand cleaning stage. This second, longer on-demand cleaning stage is intended to be the key performance test of the dust collector and lasts for 20 hours. Stage 5 is the upset condition stage. This stage turns the cleaning system off and continues to feed the dust until the differential pressure reaches 10 inches of water gauge. As most dust collector owners know, and all dust collector manufacturers know, upset conditions can happen. The goal of Stage 5 is to evaluate how well the dust collector and the filters handle an upset condition of elevated pressure drop. It is during these times of elevated pressure drop that gaskets and filters can fail. After the upset condition has been reached, Stage 6, the post-upset condition stage, begins. This stage reduces the airflow to 25% of specified airflow, pulses each filter 10 times, and then returns the airflow back to 100%. The goal of Stage 6 is to evaluate how well a system can recover after an upset condition. The dust feed and on-demand cleaning are then resumed for at least one cleaning cycle, and then the test is completed. The Standard 199 system setup is shown here in the schematic. The standard identifies all of the necessary components and their locations from the dust feeder, dust injector, piezometer rings for pressure ports, emission sampling ports, airflow measuring device, and blower system with afterfilter. The standard requires the system to be leak tested after the outlet of the dust collector to ensure no leakage would impact the airflow or emissions data. The standard requires 2 types of emission monitors, gravimetric and photometric. Gravimetric is a simple tare weight analysis of an EPTFE membrane filter before and after each stage. The photometric sampler is a light-scattering aerosol photometer calibrated to the test dust and measures the size and quantity of the particulate emissions. The Standard 199 thoroughly details the various aspects of each item in the system test setup. There is only one requirement that constrains the design of the pulse clean dust collector, and it requires that a maximum of 25% of the filters can be cleaned during any pulse cleaning event. What this means is that the dust collector needs to have a minimum of 4 pulse cleaning valves so the results cannot be skewed. The test dust specified shall be fine ground calcium carbonate, also known by the trade name Adamite. The particle size is 0.3 to 10 micron with a 3 micron median. The bulk density is 40 pounds per cubic foot loose and 65 pounds per cubic foot packed. A fun fact about the test dust and the testing at SDC is that when we completed the testing, we donated the test dust to a local park district for them to use as baseball diamond chalk, over 1,700 pounds worth. While the testing process and stages are identified by the standard, many testing parameters are identified but not specified. The parameters include airflow measured in actual cubic feet per minute, or ACFM, filter media type and total surface area in square feet, which will also determine the air-to-cloth ratio, the pulse cleaning system settings from the high and low DP set points in inches of water gauge, off time between pulses in seconds, on time or length of pulse in milliseconds, and pulse cleaning system pressure in PSI. The Standard 199 allows the test requester to specify all of these parameters. The results from the Standard 199 testing focus on 3 key parameters: emissions, differential pressure average, and compressed air consumption. Emissions data is critical to both the manufacturer and the end user for their environmental permitting and reporting. For the Standard 199 testing, the sizes of the particles are measured by the aerosol photometer that measures and records size-segregated mass fraction concentrations in the following sizes. PM10 is coarse particles less than 10 micron in diameter, PM2.5 is fine particles less than 2.5 micron in diameter, and PM1 is very fine particles less than 1 micron in diameter. The emission concentrations are measured in milligrams per cubic meter per Standard 199. In the United States, it is more common for environmental permits to be in grains per dry standard cubic foot. The chart here shows the conversion between metric and imperial units. 0.004 grains per dry standard cubic foot is the common emission standard in the U.S. and is equivalent to 9.15 milligrams per cubic meter. Differential pressure is measured across the tube sheet of the dust collector in inches of water gauge. The tube sheet, also called the cage plate, is the physical barrier that supports the filters and separates the clean and dirty sides of the dust collector. The DP is the measure of the restriction the filters place on the system. A system with a lower stabilized differential pressure will have lower energy costs realized in fan horsepower and will typically have longer filter life. Compressed air consumption is a function of the number of pulses of the cleaning system and is measured in cubic feet. For each stage, the total number of pulses is recorded and multiplied by the average air volume used per pulse. Standard 199 derived an equation creating a dimensionless ratio using the data from the last 4 hours of stage 4. This equation takes into account the total compressed air used over the amount of air filtered during the last 4 hours of stage 4. This dimensionless ratio indicates the effectiveness of the pulse cleaning system. When comparing dust collectors, the dust collector system with the superior cleaning system will report a lower ratio value. The Standard 199 also contains a report template that requires all fields to be completed and is intended to be a brief summary of the full-scale test. The report is a 3-page review that contains a macro examination of stages 1 through stage 6 and a close examination of stage 4, including a focus on the last 4 hours of the stage, which is intended to be the key performance test of the system. SDC completed the testing in its own in-house lab that was specifically built for the ASHRAE 199 standard. To SDC, it is important that the testing be completed on a dust collector from our standard product catalog and not a special dust collector designed specifically to fit and function for the standard. For our SPJ PulseJet baghouse line, there are 2 types of designs, top removal filter and bottom removal filter. The top removal filters are more widely used and therefore SDC selected the smallest standard collector from our top removal product line, the SPJ 40 X4 RT6. After selecting the baghouse model to test, SDC then determined the Standard 199 test parameters. The SPJ 40 X4 RT6 has 5 pulse valves and meets the 25% maximum cleaning requirement. SDC selected industry standard singed polyester bags to operate at our higher air-to-cloth ratio. Here, SDC chose 3000 CFM for an air-to-cloth ratio of 10.6 to 1, which is standard for SDC but double for the industry, which is 5 to 1 for this application. SDC then determined the pulse cleaning system settings and then using 3000 CFM determined the amount of dust required to meet the requirement of 1 grain per cubic foot at the specified airflow from standard 199. On January 22, 2020, SDC started Test 1 of the ASHRAE Standard 199 test procedure. On January 24, 2020, SDC concluded Test 1. The following will be an in-depth analysis of all stages of the Standard 199 testing and a look at the results using the Standard 199 report template. The initial pressure drop for Stage 1 was 0.24 inches of water gauge using clean bags at 100% airflow before any dust was fed into the system. Once the dust was introduced into the system, there was an initial and brief spike in emissions. This emission spike is expected as the pores of the media are wide open. However, as the pressure drop slowly started to increase and as the filter cake forms, the emissions drop quickly. Stage 1 lasted for about 35 minutes. As mentioned earlier, the emission standard in the U.S. is to be less than 0.004 grains per cubic foot, or 9.15 milligrams per cubic meter, which is represented by the red line. For Stage 2, the cleaning system was turned to on-demand. The pulsing of one of the 5 diaphragm valves cleaned 20% of the filters and reduced the DP well below the low limit setting of 2.6 inches of water gauge. During the first complete cleaning cycle where each valve pulses once, there are spikes in emissions up to 21.6 milligrams per cubic meter, which is to be expected. During the second complete cleaning cycle, the emission spike is reduced by 44% down to 12.1 milligrams per cubic meter. All of the subsequent cleaning cycles and pulses do not see any spikes in emissions above the 9.15 milligrams per cubic meter red line. Stage 2 lasted for 4 hours. The results of Stage 3 confirm that the initial dust loading in Stages 1 and 2 were a complete success. Once the system entered in continuous cleaning, the emissions reached a maximum of 8.92 milligrams per cubic meter, which is below the 9.15 milligrams per cubic meter emission standard. As the results show, there are 2 trends emerging. The differential pressure is trending towards a low stable pressure drop, and the emissions are trending towards an extraordinarily low amount. Stage 3 lasted for 24 hours. The results of Stage 4 confirm the difference between on-demand cleaning and continuous cleaning. Lower emissions, less compressed air usage, less wear on the filter media due to less cycling of the filters. During Stage 4, the emissions reached a maximum of 0.1012 milligrams per cubic meter, which is almost 2 orders of magnitude less than the emissions rating of 9.15 milligrams per cubic meter. This stage lasted for 20 hours. The goal of Stage 5 is to evaluate how the dust collector and the filters handle an upset condition of elevated pressure drop. Here, the SDC SPJ bag house was able to endure the 10 inches of water gauge upset condition with ease, and there are no signs of dust leakage or filter failure. This stage lasted for about 36 minutes. In Stage 6, after 10 complete cleaning cycles, the DP dropped from 10 inches of water gauge down to 0.74 inches of water gauge at 100% airflow. Testing resumes, and there is a relative spike in emissions up to 1.36 milligrams per cubic meter, which is almost 1 order of magnitude less than the 9.15 milligrams per cubic meter. On-demand cleaning is resumed for 1 cleaning cycle, and then Stage 6 and the tests conclude. Now on to the Standard 199 test report. On page 1, there's identifying information and a Stage 1 through 6 chart of differential pressure and emissions over time. On page 2, all of the test requester information, system parameters, test conditions, and test results are summarized. On page 3, there are different charts examining differential pressure, compressed air usage, and emissions along with any comments from the tester. To ensure SDC met the Standard 199 protocol, SDC sought a third-party review. SDC Laboratory and ASHRAE 199-2016 testing protocol have been audited and certified by Blue Heaven Technologies on September 17, 2020. Blue Heaven Technologies is an industry leader in filtration testing with their own Standard 199 lab. Also, they are led by Robert Burkhead, who serves as a ranking and voting member on the ASHRAE Standard 199 Project Committee. In conclusion, SDC's higher air-to-cloth ratio design is different. Typical air-to-cloth ratios for fine powders like the Standard 199 test dust for the generic bag houses are 5 to 1. For the Standard 199 testing, SDC operated at 10.61 using our standard design features, a supersonic nozzle cleaning, high side inlet, and wider bag spacing. Superb collection efficiency at all PM levels, low system pressure drop, and upset condition recovery are all well proven and documented. For more information on ASHRAE 199 and to get a copy of the summary or full test report results, visit our website www.scientificdustcollectors.com.